week after our quiz on gravitation. We started to talk about satellites, satellite motion. And what I'd really like to specifically get at is a quick reset of what a satellite is, discuss the things that determine the speed and properties of a satellite. I'm going to refer to this probably more than once, that every orbit, depending on how far it is away from Earth, every orbit has a speed limit. And we're going to see how the velocity, that speed limit, and the radius of that orbit determine the period on some level, the time for one trip around the Earth. So let me go to a transparency in the book, and then we'll go back and derive the equation that governs the speed. Before I do either, I just want to remind you that a satellite is simply an object that's moving fast enough tangentially so that as it falls, it doesn't get closer to the Earth. It simply falls around the Earth and maintains the same altitude. We have thousands of satellites in orbit that we've placed in orbit and other nations have placed in orbit, but the most famous satellite, of course, is our moon. Let's look at the speed that a near-Earth orbit, a low Earth orbit has, and how it's really just affected by the geometry of the planet we live on, Earth, and the acceleration due to gravity. This is a lovely little color transparency from the materials our textbook provided teachers, and you saw it in the book when you read after the quiz. I just want to reset a point, and that is that objects on Earth fall about 5 meters in 1 second. We've been a little more precise about that. We've said that distance an object falls is equal to the initial velocity times time plus 1/2 at squared. And of course, if you drop it or throw it horizontally, it has no initial vertical velocity. And so this just becomes 1/2 at squared. And of course, a on Earth is negative 9.8. And in 1 second, the time elapsed would be 1 second. 1 squared is 1. 1 times 9.8 is 9.8 negative. And half of that would be negative 4.9. Your author just rounds it to 5 for brevity, to make it simple. So here we have the gal throwing it softly, and it travels in this arc, throwing it faster, and it follows this arc, and still faster, it follows this arc. And you'll notice that this ball doesn't quite reach the ground because, of course, the Earth is not flat. If the Earth were flat, then all these balls have the same vertical displacement after 1 second. But of course, the Earth is curved. And so this ball is still not quite to the ground. And the point is, because of the geometry of our planet, because of its radius, precisely because of its radius, for every 8,000 meters you go horizontally on Earth, the Earth's curvature drops by 5 meters. And we've already talked about how an object falls 5 meters in 1 second. So this gets at why the magic velocity to be in orbit at a near Earth orbit, a low Earth orbit, not high above the Earth, but only a few 100 kilometers above the Earth, the magic velocity to do that is 8,000 meters per second. Because every second, if you're going 8,000 meters per second, you go 8,000 meters horizontally, and you fall 5 meters, but because the Earth has curved by 5 meters, you remain at the exact same altitude, the same height above the ground. So for low Earth orbit, to summarize, orbital velocity is 8,000 meters per second. Now it's actually 7,990, but again, our author rounds up. Incidentally, if you were to go 8,000 meters per second, you would orbit the Earth and you would take about 90 minutes to make one trip around the Earth. 90 minutes, an hour and a half. So perhaps I've let the cat out of the bag. I've told you that it's 8,000 meters per second. But what if the orbit were higher? What if it were a satellite that's halfway to the moon, orbiting the Earth, but halfway between the Earth and moon, at 30 Earth radii away? That's certainly farther away than one Earth radius, or slightly more than one Earth radius, as is the case with like the International Space Station, for example. So let's see if we can derive this equation. Your book is a strong book conceptually, but it lacks, I believe, this equation. So let's look at what's going on. So this satellite travels with some velocity v, and it is acted on by the force of gravity. Now, backing up a little bit to chapter 10, if this satellite is moving in a circular orbit, and many satellites move in a perfectly circular orbit, or very, very close to it. If it's moving in a circular orbit, then there's a centripetal force. There's a centripetal force acting on that satellite. What provides that centripetal force? We've seen balls on strings where the string is pulling toward the center. We've seen problems with cars going around a curve where friction provides the centripetal force. But what provides this centripetal force that I'm going to call Fc? Well, in the case of an orbiting satellite, it's the gravitational force of attraction of the Earth. I want to remind you that centripetal force is mv squared over r, where this is the mass of the satellite. Let's call it object 1. And the gravitational force is big G, the universal gravitational constant, m1, m2, in this case the mass of the Earth is m2, over the distance between them squared. And for a low Earth orbit, let's just pretend like it's a treetop orbit very close to the Earth, and call the height the radius of the Earth. Because the centripetal force is provided by gravity, they are the same force. The centripetal force is gravity, and gravity is the centripetal force. I don't know which way you want to say it. So if we go ahead and set mv squared over r, the centripetal force, equal to the gravitational force g m1 m2 over distance squared. Now, honestly, I'm going to call the distance r, because in a minute you'll see that that's a valuable thing to do. So I'm just saying this is a low orbit. Either way, these are the same number. The radius at which this centripetal force acts is the center to center distance. This distance is the center to center distance. So for the sake of argument, let's just start using the r notation. Recall that the object experiencing the centripetal force is the satellite. So m1 is the mv squared over rm, and m1 is here as well. Recognizing that these are the same mass, m1, they can be eliminated by division, cancel, if you will, as can, this is really r times r, and this is r, and since they're both on the denominator, this square is canceled by this r. For those of you that didn't like that, r squared is really just r, and this is r, and so one of these cancels one of those. That leaves a single r. Let's rewrite this as v squared equals g m Earth over r. m2 is the mass of the Earth in this case. And for any satellite orbiting the Earth, that m2 will be the mass of the Earth. Taking the square root of both sides leaves us with v, the speed of the satellite, is equal to the square root of the universal gravitational constant, big G, the mass of the orbiting object, the orbited object, in this case the Earth is being orbited, over the radius of the orbit. And again, if for a low Earth orbit, this would be the radius of the Earth. For a satellite that's 2 Earth radii away, this would just be 2 times the radius of the Earth. This is the radius of the orbit. But for a low orbiting satellite, you probably just plug in the radius of the Earth. So we've gotten to exactly why this statement, every orbit has a speed limit, is an interesting, valuable thing to say. G is a constant. It never changes. It doesn't matter where the satellite is, whether the satellite is the moon. G is just G. And the mass of the Earth doesn't change depending on how high the satellite goes. The mass of the Earth is simply the mass of the Earth. So it is solely the radius of the orbit that determines the speed of the satellite. Notice that the satellite's mass doesn't matter at all. It canceled from the expression. We canceled M1. We canceled M1. You could be orbiting a toaster or a Nike shoe at the same altitude as this satellite, and they would both require exactly the same velocity, or speed I should say, at the same orbital radius. Let's go ahead and do a sample problem and put this equation into effect. This is a good equation for you to write down at the bottom of page 1 of our packet, because of course at the bottom of our packet it said what determines the speed of a satellite in a circular orbit. Is there an equation that shows the governing factors in a clear way? Also, this is redundant, but it says your teacher may have said, you may have heard, every orbit has a speed limit. What does this mean? Is there a new formula? And this is the new formula. So I'm going to pause for a minute, and Ms. Durson may pause the video itself to give you a chance to get that down in your packet. It also is on the very back of the packet on top, because it's the first equation that we're going to look at in this chapter. Let's do that sample problem. This sample problem appears on page 3 of the yellow packet that I was just waving around, the chapter 14 homework packet for the chapter. It starts out by saying the ISS, the International Space Station, is in an orbit above the Earth at a distance which is measured from the center of the Earth to be 6.79 times 10 to the 6 meters. Now the mass of the International Space Station, when complete, will be 4.196 times 10 to the 5 kilograms. Now the Earth's mass we're acquainted with because we've been doing gravitation problems with this number is 5.98 times 10 to the 24. What is the orbital speed of the ISS? I get kind of carried away with subscripts sometimes. You're looking for V. Now we just saw that the speed of a satellite in a circular orbit is equal to the square root of the constant G, the mass of the Earth, and the radius of the orbit. So you'll notice right away that we have two masses, and one of them is irrelevant. Again, it wouldn't matter if a toaster, a school bus, or a Maserati were in orbit at this radius. It doesn't matter what the mass of that object is. So I'll plug these in real quick. V equals 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times the mass of the Earth divided by the radius of the orbit, 6.79 times 10 to the 6 meters. R was squared in our gravitational formula, but we eliminated the square when we solved for this, so this is not a squared thing. Of course, all of this is under the square root. 6.67 times 10 to the minus 11 times 5.98 exponent 24 equals, divided by the orbital radius of the space station, in this case 6.79 times 10 to the 6th. I'm going to hit equals, but that just leaves me with everything under the square root. I still have to hit square root, so I'll do that now. And we get 7,664 meters per second. Calculate the period, the time, capital T, for one orbit in seconds. Now, thank goodness, because this is Newton meter, I didn't analyze the units carefully, and I don't want to do that right now. But you might recall that a Newton is a kilogram meter per second squared. So we're already working with units that have seconds in them, as you can see that the velocity is in me. I can show you in class when I come back that this really does come out. All of this is meters per second. But period, that relates to a circular orbit or any kind of circular motion by virtue of the equation that V equals 2 pi r over t. Now, you may recall that when something equals a fraction, you can just switch places with the thing that's on the left in the denominator term. So with that switch, t is equal to 2 pi r over v. So there's a more complicated way to do this, but this is the easiest way to do it, because we know v now, we know r, and we want t. I kind of wrote the unrounded version of the velocity that I rounded off here, but the calculator has the unrounded version, so I kind of went to 5 digits. Anyway, let's go ahead and 2 times pi times 6.79 exponent 6. That's the numerator of this expression. And now I'm going to divide by, recall 1, 7,664.4. When I hit equals, I get 5,566 seconds. Now, earlier I told you, and that's the answer at the bottom of this section, but a moment ago I said it takes about an hour and a half for an object in a low Earth orbit to make one trip around the Earth, the International Space Station, for example. Let's see if, how many minutes is this 5,600 or 5,566 seconds? Is it close to an hour and a half? Well, we know that there are 60 seconds in a minute. So if we want to convert the 5,566 seconds to a minute value, let's just turn it into a fraction by putting it over 1. You'll see in a moment why I think that's a good idea. And now I'm going to multiply by the relationship that links seconds and minutes. And keeping in mind that I want my answer to come out in minutes, that means I need minutes to be on top, and I want the seconds to go away. I want those to disappear, so I need to put seconds on the bottom. Because if I put the right relationship here, these seconds will cancel, cross-cancel. So what is the relationship? Well, of course, 1 minute is 60 seconds. So having done this conversion, so to speak, I see my units are going to cancel, leaving minutes. Now what I need to do is divide the 5,566 by 60, because 5,566 times 1 is that, and 1 times 60 is 60, so it's really this divided by that. Let's do that, divided by 60. And sure enough, it's about an hour and a half. It's 92 0.77 minutes. I'm going to round that off to just 92.8 minutes. So you'll see we've sort of done our first big sample problem on satellite motion. I think at this point the best thing to do is see a video on Kepler's laws. I really deeply regret not being here to watch that video with you. It's an important film for many reasons, and I got to be careful to not get more long-winded because I know you've been watching this video for over 20 minutes. But Kepler came at a time before Newton, so what he achieved with the development of his three laws did not benefit from the idea of forces acting over long distances, pulling planets around the sun and moons around their planets. He truly did not have that mental construct yet. Humankind did not know. So it's all the more remarkable that he developed these laws without those tools. In the video, they're going to talk about different models of the solar system. The Ptolemaic model, the Copernican model, the Tychonic model. These all refer to people. Ptolemy, Tycho Brahe is in the video. You'll see about his contribution to Kepler's laws. There's the Platonic model, and then what we now believe to be accurate, the Copernican model. I just edited the video and I want to add one thing. Plato, who was a Greek thinker long ago, had an idea that all motion in the heavens, in what we now know is our solar system and beyond, all that motion that he thought was circular and revolved around the Earth. So the Earth was at the center, was immobile, sitting there, and everything moved around us. A celestial sphere rotated. It was complex, but wrong. It didn't explain what we came to see the harder we looked with telescopes and things like that. So you're going to hear the Platonic dictum, and that's just this belief from Plato that motion in the heavens was circular. A Polish monk named Nicholas Copernicus came along. He died in 1543. The same month his book was published. And in that book, which he was afraid to publish because the Roman Catholic Church agreed with the Platonic dictum and said that that is how it is, so disagreeing with the Platonic dictum was a crime, Copernicus correctly, for the first time, saw that the planets moved around the sun. Now there were other models in between. Ptolemaic model, we'll talk more about that. There was a Tychonic model that had to do with a gentleman who's in the film in important ways named Tycho Brahe. And I did some research on Tycho Brahe. He was a Danish astronomer. And you're going to see some things in the movie you just have to understand. So Tycho or Tycho Brahe, and I put some people up whose birth and death dates may help you get context. Tycho Brahe was this Danish noble person, wealthy, related to the king. And if you look at his Wikipedia page, it's quite interesting. They actually exhumed his body in 2010, so 12 years ago. They dug his body up to answer some questions about whether he was poisoned. There was some suspicion that Kepler may have poisoned him. It turns out it's very unlikely that he died from a murder, that he simply was sick. At any rate, you're going to see in the movie that he has a gold nose. Another interesting thing about him is he got in a sword fight, a duel, with his third cousin when he was 20, over an argument about who was the better mathematician. And part of his nose was cut off in this sword fight, in this duel. So he wore for most of his life a prosthetic nose when he was in public. and you'll see in the video it's gold. It turns out he had a gold, a silver one. He only wore those on special occasions. The one he wore every day was likely made of brass, which they found out when they did this autopsy 12 years ago on his 300-year-old body, and found a bunch of brass, in the bridge of his nose. Anyway, I'll let you see the video, but I thought you might want to know a little bit about these folks. I'd like Ms. Durson to pause the DVD player at this time and pass out the film question. I think it'll just help you stay focused on the film. And so hopefully those are not annoying to you, but help you kind of pick up some of the pieces of the film that I want you to see. And I'll see you on Thursday, the 3rd. Thank you.
Studying the orbit of Mars around the Sun, Johannes Kepler discovered its path could be explained only if the planet traveled along an ellipse. It was the first of Kepler's 3 laws.
I'm sure you remember that Tycho Brahe had his own system of the universe. In the Tychonic system, the Earth was stationary at the center, the Sun went around the Earth, and all of the other planets went around the Sun. Of course, Tycho believed passionately in his own system, and on his deathbed, he begged Johannes Kepler to use the new observations to prove the correctness of the Tychonic system. It was a touching moment. I have no idea of what Kepler thought of that moment, but the idea of doing what Tycho had asked him to do never even crossed his mind. Kepler was a Copernican to his very core. And as soon as he got his hands on Tycho's data, the first thing that he set out to do was to analyze the orbit of Mars. It proved to be enormously difficult, and no matter what he did, he couldn't make the orbit of Mars fit a circle. The disagreement between the angular position of Mars in the sky and the best circular orbit was 8 minutes of arc. In other words, if he had tried to do the same thing before Tycho's observations, it would have been possible. But with the new data, it could no longer be made to work. And so Kepler was faced with a direct conflict between the ancient Platonic dictum that all motions in the heavens had to be circular motions and the new Tychonic observations. Faced with that conflict, he made his choice. He chose the observations, and he started to search for a different smooth curve that would describe the orbit of Mars. After years of agonizing work, he hit upon the answer. It was a curve that had been known for thousands of years, and it's called an ellipse.
In the most graphic terms, a piece of string and 2 pins illustrate the simple elegance of an ellipse. Since the string doesn't stretch into a different length, the total distance from one pin to the pencil to the other pin is constant. A single point is called the focus. 2 points, the foci. The length of the semi-major axis is A. The semi-minor axis has the length B. The region bounded by the ellipse has area pi AB. The distance from the center to either focus is some fraction of A, EA. The symbol E represents the amount of eccentricity. As in the social context of the word, eccentricity means somewhat off-center. So when E shrinks to 0, when there's no eccentricity, the result is a perfectly rounded figure, an ellipse called a circle. But when E increases, the ellipse becomes increasingly eccentric and increasingly flat. Focus is the Latin word for fireplace. It was first used for the ellipse by a man who became known as the wandering mathematician. His name was Johannes Kepler. And in the sun, he saw the greatest fireplace in the universe. At the dawn of a new century, January 1st, 1600, Kepler set off in search of the most accurate astronomical data on Earth and the man who possessed them, Tycho Brahe. Born into the let-them-eat-cake class of society, Tycho surprised Danish nobility with his decision to do something worthwhile. His penchant for astronomy became his reason for living, and for the last 38 years of his life, he charted the heavens with extraordinary precision. No one on Earth appreciated the potential value of Tycho's heavenly observations better than Johannes Kepler. To him, the data were essential, the key to unlock the door to the universe and to reveal what he called the secrets of the skies. But much to Kepler's dismay, Tycho knew how to keep a secret. So Kepler struggled without Tycho's precious data for almost 2 years. Then, on October 24th, 1601, fate stepped in. Tycho's dying words were, "Let me not seem to have lived in vain." The Danes' family withheld the data, but Kepler managed to make Tycho's last wish come true. Advancing science more than ethics, he stole the material. The otherwise mild-mannered little mathematician was finally ready, in his own words, to wage my war on Mars. Mars, the red planet. Mars, an early Roman god of agriculture and of war. Mars, through the ages, powerful and mysterious. Within the ancient world's concept of the Earth-centered universe, the planets moved in epicycles, and sometimes, as with Mars, the epicycles were very erratic. To account for such erratic behavior, Tycho conceived his own universe, the Tychonic solar system. Like Ptolemy, he placed the Earth at the center with the sun revolving around it. But like Copernicus, Tycho had the other planets orbiting the sun. While Tycho's system fit the appearances more simply than Ptolemy's, Kepler passionately embraced the views of Nicholas Copernicus. This was not only an unpopular view, Galileo would be tried in Rome for sharing it, it was an extremely difficult one to justify scientifically. Consider the Copernican solar system and the problems it presented Johannes Kepler. From Copernicus's revolutionary viewpoint, Kepler had to make mathematical observations from a planet that, rather than being central and stationary, was in motion with all the other planets. Imagine the difficulty of trying to compute the orbit of Mars from a moving platform, a platform that spins on its axis, in a non-circular orbit, with constantly varying velocity, and with an unknown center. This was Kepler's dilemma, and he approached it with a poetic faith in a logical universe. Kepler seems to have been created to calculate, and his calculations, which totaled over 900 pages, were enormously difficult. His war on Mars was a patient siege in which many of his weapons were imperfect and faulty, but he employed them with a striking brilliance. For example, to find the location of his moving platform, Kepler used observations of Mars as it returned, Mars year after Mars year, to the same point in its orbit. Then he reversed them to find the orbit of the Earth. By finding a circle, even though it wasn't quite centered on the sun, Kepler had taken a step in the right direction. So now, once again, he attacked the problem of Mars. Still unable to find its exact path, he did manage to find something suggestive in its irregular speed. Mars moved faster when it was closer to the sun and slower when it was farther away. This would become Kepler's second law, but he still hadn't found his first law. Approximately every 2 years, the sun, the Earth, and Mars are in opposition. In other words, seen from either the Earth or the sun, the position of Mars is the same. With another observation, 1 Mars year later, Kepler could triangulate a precise point on the orbit of Mars. Could a circular orbit, even one offset from the sun, fit all of the points? Almost, but not quite. That is, not within the unparalleled precision of Tycho Brahe's observations. What curve, then, would describe the orbit? The answer to that question revealed the secret of the heavens. With the sun at one focus, an oval orbit, a slightly distorted circle was called for. And that type of orbit was an ellipse. The ellipse, known to the ancient Greeks and finally rediscovered in the heavens by Johannes Kepler, can be viewed time and time again right here on Earth. It's simply a matter of looking at things in the right perspective. Any circle, viewed obliquely, appears as an ellipse. The Greeks knew the parabola and the hyperbola, as well as the ellipse. By slicing a cone with a plane, they generated curves called conic sections. If the cutting plane is perpendicular to the axis, it cuts out a circle. When the plane is tilted, the circle becomes an ellipse. Tilting it enough for the plane to be parallel to a side of the cone produces a parabola. Tilted farther, the conic section becomes a hyperbola. Of course, Johannes Kepler never imagined that the hyperbola and the parabola could be found in the heavens. In fact, his use of the ellipse for the orbit of Mars was possible only because it was the only planetary orbit eccentric enough, about 9%, to be noticeably non-circular. Had Kepler waged war on any other planet, he probably would have died believing that circles reign supreme throughout the universe. But of the battles he had an opportunity to choose, he chose well. And with Tycho's data, he was victorious in the knowledge that the ellipse, as perfect a fit as could be measured, was the mathematical secret of God's creation. These secrets were revealed, perhaps even paraded as the spoils of the war with Mars, as Kepler's 3 laws. Kepler's first law states that each planet moves in an ellipse with the sun at one focus. While waging war on Mars, Kepler found his second law. A line from the sun to a planet sweeps out equal areas in equal times. Kepler's second law permitted astoundingly accurate computations of distance and velocity. His third law came 10 years later. It states that the square of the period of a planet is proportional to the cube of the length of the semi-major axis, and it reveals a connection between the motions of different planets.
Although Kepler's geometric model was incorrect, it led him to discover 3 laws that describe the heavens with precision. Each planet orbits the sun along an elliptical path with the sun at one focus. A line from the sun to a planet sweeps out equal areas in equal times. The square of the period of a planet's orbit is proportional to the cube of its semi-major axis. These are Kepler's 3 laws.